Okay, today we shall be talking about spurious regression model and co-integration and error correction mechanism. That we shall be talking today. Spurious regression, co-integration and error correction mechanism. And it is under model 1. Okay, before talking it, we first talk about some theory. What is the theory? Regression of a non-stationary time series. Regression of a non-stationary time series on another non-stationary time series may cause spurious regression or nonsense regression. A spurious model is not desirable all the time. So what is happening here? If the variables are non-stationary, and then if we estimate the regression model, probably that model is spurious or nonsense. So we cannot accept that model. Okay, here we talk about our model. In our case, we have two variables such as ex and cons, and they have unit root at a level, meaning non-stationary. So what is happening here? We have two variables such as ex and cons, but we assume that they have unit root at level, or these two variables are non-stationary. Suppose we assume that they are non-stationary, but we also assume that they become stationary after first difference. Suppose we assume that they become stationary after first difference. That is also our assumption. What is our assumption? Our assumption is our two variables ex and cons have unit root at a level, but when we convert these two variables into first difference, then they become stationary. That is our assumptions. Okay, and here ex means export and cons means consumption, right? That is the thing. Ex means export and cons is consumption. Okay. Okay, now if we run a regression model with these two non-stationary variables, the estimated regression model may be spurious or nonsense, like model 1.1 below. That means this model model 1.1 can be spurious because ex and cons both are non-stationary. Okay, what is the symptom of spurious model? The symptom of a spurious model is R square value would be greater than Durbin-Watson statistics. So that is the guideline of a spurious model. If the value of R square is more than Durbin-Watson statistics, then the model becomes spurious or nonsense. Okay, what we have done, we have estimated model 1.1. After estimating model 1.1, R square value has been 0.72, while Durbin-Watson statistics stood at 0.70. So here what is happening? R square is more than Durbin-Watson statistics. So it means that our estimated model 1.1 is a spurious model which is not acceptable. Okay. So model 1.1 is a spurious, we cannot accept it. But if the residual of the model 1.1 is found stationary, in that case model 1.1 is no longer spurious or nonsense. We can accept the model. Meaning that what I want to say here, after estimating model 1.1, if the residual of the model 1.1 is found stationary, then model 1.1 is no longer spurious. We can accept the model. So the residual must be stationary. Okay, actually here are two conditions. Number one condition, that Ex and cons, these two variables must be non-stationary at level, and they will become stationary after first difference. That is the number one condition that will have to be. And second is the residual of the model 1.1 should be stationary. And if it is happen, then model 1.1 is no longer spurious or no longer nonsense. So we can accept the model. Okay. And there is some more thing. If the residual of the model 1.1 is found stationary, it also means that variables in the model 1.1 such as Ex and cons are cointegrated, or they have long run relationship, or they have long run equilibrium relationship between them. In other words, model 1.1 is a long run model. So here what is happening? If the residual is stationary, then what will happen? The estimated model 1.1 is no longer spurious. We can accept the model. And secondly, if the residual is stationary, then the variables of the model 1.1 are cointegrated, right? Variables of model 1.1 are co-integrated, or they have long run relationship, or they have long run equilibrium relationship between them. So model 1.1 is a long run model in that case. So it is a long run model if the residual is stationary. And here so if the residual of model 1.1 is stationary, then model 1.1 is a long run model, meaning that the B2, the coefficient of cons, actually this B2 would be long run coefficient. B2 would be long run coefficient, not short run coefficient, because the whole model will be long run model. And after estimating model 1.1, B2, the coefficient of cons variable of model 1.1 is a long run coefficient, and the value of the B2 has been 5.69, and also this coefficient is significant after estimations. Okay, now we want to check whether the residual of model 1.1 is stationary or not. How to check it? And you know that how to check whether a variable is stationary. So we can use the augmented Dickey-Fuller test to check whether a variable is a stationary or not, or our residual is stationary or not. So we can check it using augmented Dickey-Fuller test. And we have already tested and found that the residual found stationary using augmented Dickey-Fuller test, meaning that EX and cons have long run relationships, or EX and cons, these two variables are co-integrated, meaning that model 1.1 is a long run model and B2 is long run coefficient. Okay, but here one thing we have done, here we need to use the Engle Granger critical value for unit root testing. So here actually we have used the Engle Granger critical value to check whether our residual is stationary or not. What is called stationary? Stationary means there is no unit root. And what does mean by non-stationary? Meaning that our residual has unit root. That is called non-stationary or unit root. And here actually we have used Engle Granger 5% and 10% critical values, that is minus 3.34 and minus 3.04 respectively, to check whether our residual is stationary or not stationary, right? Okay, so what we have seen, actually we have seen our two variables such as ex and cons have long run equilibrium relationship, or our two variables are co-integrated, that we have seen. Okay, and when the variables are co-integrated, then we can run the error correction model. Error correction model only we can run when the variables are co-integrated. So as the variables such as ex and cons are co-integrated, we can run the error correction model as below, model 1.2. So this one is our model 1.2 and this one is the error correction model. And here you see ex is the dependent variable. So in the error correction model, the data, the variable must be stationary. The variable must be stationary. So what I have done, I have converted ex into first difference, right? Dex. Dex means first difference of x, first difference of ex. So this variable become first difference of ex, or this variable becomes stationary. And then B3, what is B3? B3 is the constant or intercept of the regression model, and B4 is the coefficient of variable decons. What does mean by decons? First difference of cons variable. That means cons variable has become stationary after first difference. And then another coefficient, which is B5. What is B5? B5 is the coefficient of ut minus 1. What does mean by u? U is ut minus 1, actually called residual. One period lag residual. That is ut minus 1. That means residual but one period lag. And what is the B3? B3 is the white noise error term. Okay, I am telling again, here ex and cons are the first difference variables. B3 is the intercept. B4 is the short run coefficient. Make sure it is a short run coefficient, not long run. So B4 is the short run coefficient, not long run. And V is the white noise error term. But here, most important thing is this one. Most important thing is here, error correction term, this one. It corrects the disequilibrium. Okay. What is it? ut minus 1. ut minus 1 is the one period lag residual of model 1.1. I'm showing again. ut minus 1 is the one period lag residual of model 1.1. Okay, here what is model 1.1? So we can go up. Last time we saw it. It is model 1.1. What we have done here, we have estimated this model 1.1. Then we have taken the residual of this model. Then we have taken 1 period lag of the residual. And that one is actually this one, ut minus 1. 1 period lag of the residual of model 1.1. Okay. Ut minus 1 is also known as equilibrium error term of 1 period lag. Okay, this ut minus 1 is the error correction term that guides the variable variables such as ex and cons of the system to restore back to equilibrium. Okay. In other words, it corrects the disequilibrium. That means error correction term actually rectify the disequilibrium in the system model. That is her task. That is her action to correct the disequilibrium in the system. But the sign before B5 or the sign of error correction term should be negative after estimation. That means the sign, you see, B5 and the sign, this sign should be negative. The coefficient B5, meaning that this one, the coefficient B5 tells us at what rate it corrects the previous period disequilibrium of the system. That means the speed of the adjustment or the speed of the correction of the disequilibrium. That is the B5. B5 tells about the speed at which it corrects the previous period disequilibrium. And when B5 is significant and contains negative sign, it validates that there exists a long-run equilibrium relationship among variables stated in model 1.1. That means when the B5 is significant and when the B5 has a negative sign here, then it validates that there exists a long-run equilibrium associationship between Ex and cons, which are two variables. Okay. And what we have done, we have estimated this model 1.2, which is error correction model. We have estimated it. After estimating model 1.2, short run coefficient value B4 has been 0.41. That means the B4 has been 0.41, but it was not significant. Okay, and B5, what is B5? This one. And B5, the coefficient of error correction term has been 20.69%, meaning that the system corrects its previous period disequilibrium at a speed of 20.69% annually. So I'm telling again, the B5 after estimating has been 20.69%, meaning that system corrects its previous period disequilibrium at a speed of 20.69% annually. So that means speed of adjustment is 20.69% annually. Moreover, the sign of B5 has been negative and significant, indicating that there is a validity of a long-run equilibrium relationship between EX and cons. Okay, so meaning that B5 is significant and negative, and the value is 20.69%, at which it is correcting its disequilibrium. And here we have only used, in the whole error correction model, we have used only one independent variable, that is cons, but in reality you can use a number of independent variables according to the need of the model. Here I show only one independent variable, but in reality you can use more than one independent variables. And model 1.2 means this model. After estimating, the model 1.2 is not a spurious model because R square is less than Durbin-Watson statistics. So it means that our estimated model, that is 1.2, was not spurious or nonsense, because when a model becomes spurious when R square value is more than Durbin-Watson statistics. But here R square value is less than Durbin-Watson statistics. So model 1.2, which is error correction model, is not spurious. And this model I call it ECM model, error correction model, is true in case of single equation model. This one is a single equation model, so we call it ECM because it is a single equation model and one-way model, right? But what is VECM? VECM happens when there is a system of equations, meaning that there are many equations. Vector error correction model, VECM, That means that means there are a number of equation which can solve at a time. So that is VECM model. So that we can discuss later about VECM model. Okay, here we have time series data of cons and ex. We have these two variable. What is cons? Cons is consumption and ex is export. So we have two variable, and I'm opening these two variable, open as a group. So it is the variable ex and cons, and from 1960 to until 2020. So it is our variable ex and cons, right? Okay, and it is our model. Okay, 1960 to 1960 to 2020. Okay, here we have assumption that these two variables are non-stationary at level, meaning that these two variables have unit root or non-stationary at level, but when I convert this variable into first difference, they become stationary. So that is our assumptions. I am telling again, when these two variable, we assume that they are non-stationary at level, but when I convert these two variable into first difference, then they become stationary. Okay, now what we shall do, what we know from the theory, that if the variables in the model are non-stationary, then estimated regression model can be spurious, or estimated regression model is a nonsense model. We cannot accept any nonsense model. Okay, and now we check whether our model using these two variable is a spurious or not. That we want to check now. Okay, we want to check now that so we estimate the regression line with this two variable, right? Okay, so how to run regression model? I go to quick, then I go to estimate equation. Okay, and here ex is the dependent variable, so I write it first, ex, then I write c, then I write cons. So this is our regression model. Ex is the dependent variable and cons is the independent variable, and C is the constant, and here both the variables are non-stationary. Okay, but the first difference of this variable is stationary, that we assume, but we have not tested it. We have not tested it, but we assume that both are stationary after first difference. And okay, now we run this model, right? So the result has come up. It is the dependent variable, right? And cons is the independent variable. It is the coefficient 5.69, and the cons is significant because the p-value is less than 5%. So the cons is a significant variable to explain our dependent variable, which is Ex. Okay, now, but the question is that whether this model, this estimated model, is a spurious or not, or whether this model is a nonsense model or not. Okay, what is the symptom of a spurious model? The symptom of a spurious model is the value of R square should be greater than Durbin-Watson statistics, right? That is the spurious model. And here, how much is the Durbin-Watson value? How much? 0.72, and which is greater than Durbin-Watson statistics, meaning that our estimated model is a spurious model because R square is more than Durbin-Watson statistics. So it is a spurious model. Okay, that means when the model is spurious, we cannot accept the model. Okay, but there is a one more thing. But if the residual of this model is spurious, if the residual of this model is stationary, then our estimated model is no longer spurious. So we should check the residual, whether it is stationary or not stationary. And here, so what is the residual of this model? You can see from here. So here it is the residual of our regression model. You can see from here. It is the residual, you see. It is the residual of the model, right? From 1960 to 2020, right? You can see from here. And if this residual is stationary, then our regression model is not spurious. Okay, so what I do? I create a variable here. I create a variable such as u. new object, then series, then I put u. You see, I create a variable which is u. And what is u? U, I put it u equal to resid. You see from here? That means u and resid should be the same thing, right? Then I press enter. Okay, so now resid and u has become same. So we are opening both to check. You see, resid and u has become the same, right? Until 2020, right? Both variable become same. Okay, now if this u is stationary, then our estimated model is not spurious. Okay, so how to check? I go to quick, I go to series statistics, I go to unit root test, then I write u. U is the residual, right? So here what I am doing, I am doing unit root testing. Okay, so augmented decay Fuller, right? So here are three options. We know already, right? We have the three options, right? Intercept, trend and intercept, and none. Okay, suppose I choose the first option, intercept, right? And the residual at level, right? Then what happens? I press OK. You see, what is our null hypothesis? U has a unit root. U has a unit root means what? It means U is non-stationary. That is the null hypothesis. And what is the alternative hypothesis? Alternative hypothesis is U is stationary. That means U does not have any unit root. That is alternative hypothesis. Okay, and what is our augmented decay Fuller statistics? Minus 3.29, right? Minus 3.29. That is the test statistics. And what is the critical value? At 1%, 3.54, 5%, 2.91, 10%, 2.59. So, but here we cannot use all this critical value. We cannot use all this critical value. Here we have to use the critical value of Engle-Granger test. From the Engle-Granger test, we shall be using the critical value, not from here. Okay, the Engle-Granger critical value at 10% is minus 3.04. I am saying again, the critical value from Engle-Granger at 10% is minus 3.04. So here I am taking 10% level. So you see here the absolute value is 3.29. Absolute value means we ignored the sign, right? The absolute value 3.29, which is greater than our critical value of Engle Granger, which is 3.04. So the test statistics is greater than critical value. So we can reject null hypothesis and we can accept the alternative hypothesis. And what is our alternative hypothesis? U does not have unit root. That means U is stationary. I'm telling again, what is the guideline? The guideline is, if the test statistics is greater than critical value, we can reject null hypothesis and we can accept alternative hypothesis. And what is our test statistics? Absolute value. Absolute value is 3.29. And what is critical value? From Engle Granger, it is 3.04 at 10%. So test statistics is greater than Engle Granger critical value. So we can reject null hypothesis. And we take the alternative hypothesis. What is alternative? The U does not have unit root, meaning that U is stationary. That means our residual is stationary. It means that our estimated model that we have just estimated is not spurious. Is not spurious, meaning that our model that we have just estimated, so I am showing that one. We have just estimated our model, that is this one. I'm coming up here, just 1 minute. I'm sorry, I'm taking my model. Where is my model? It's coming up. The model is here, that is at the below, I guess, equation. Yes, yeah, this model that we have estimated is not spurious because residual of this model has become stationary. Okay, so what does it mean? It means that if the variable is non-stationary, still we can run the regression model provided the residual of the model becomes stationary. That is our teaching from here. But one thing also should be there. Although the variables are non-stationary at level, but they should be stationary at first difference. That is also should be there, so that we can use the non-stationary variables to run our regression model. Okay, now what is happening? So when the residual of this model becomes stationary, it has also another meaning. It also means that Ex and cons, these two variables are co-integrated, meaning that these two variables have long-run equilibrium relationship. I am telling again, when the residual of this model becomes stationary, it means that Ex and cons are co-integrated, meaning that they have a long-run relationship. That means the whole model is a long-run model. Long-run model, and 5.69 is a long run coefficient, not short run. This one become long run coefficient, and we can see it is significant. We can see significant. And the thing is that when the variables are co-integrated, then we can run the error correction model. I'm telling again, when the variables become co-integrated, or when the variables have long run equilibrium relationship, we can run for co-integration model. Okay, so what we have seen in this model, we have seen that our two variables such as ex and cons are co-integrated. So now we can run the error correction model. Okay, now we shall develop the error correction model. So how to develop, how to write error correction model. So mm, so uh, so error correction model is something like this. I go to quick, then I go to estimate equation. Okay, error correction model should be, the data should be in first difference. You see, ex, I write it dex. That means it is the first difference, meaning that ex becomes stationary because the data, because the variable has already converted to first difference. Then I write C, which is intercept of the regression model. Then I put our next variable, which is cons. What is cons? Cons is the independent variable. And what is decons? Decons is the first difference of cons variable, meaning that cons has become stationary after first difference. And then I draw the error correction model, error correction term. What is that? That is u minus 1. What does it mean? U minus 1 means 1 period lag of the residual. Last time, can you remember? Last time we developed this u, right? Last time we created the u. What is the u? U is the residual of the regression model, such as this one, the residual of this regression model, that is u, and 1 period lag. So when I do it, this one is called error correction model. So I'm telling again, here ex is the dependent variable and cons is the independent variable, and 1 period lag of the residual is also another variable, and this one is called error correction model. And u, 1 period lag, is called error correction term. And what is u? Residual of this model that we have estimated already, right? Okay, now we can run this error correction model and see what happens. Okay, and you see this one is called ECM, error correction model, because here is only single equation. It is not VECM. What is VECM? VECM is vector error correction model, which should have a number of equations that can be solved at a time. But here, in case of ECM, it is only one equation, one-way causation. That is why it is ECM, not VECM. And here I have used only one independent variable, but if you want you can use a number of independent variables, right? That you can do. However, I run the model. Okay, so this is the outcome of the model. You see from here. So dEx is the first difference of Ex, and it has become stationary. So, and C is the constant, dcons is the first difference of cons, which has become stationary. We assume that last time I said that first difference of Ex and cons is stationary, right? And in the time series data, we should use the stationary variable, and it is the error correction term, 1 period lag of the residual from the previous regression model. Okay, here dcons is what? This coefficient is not long run coefficient. 0.41 is a short run coefficient. And is it significant? No, because the p-value is 59.96%. The p-value is 59.96%, which is more than 5%. So short run coefficient, that is dcons, is not a significant variable to explain our dependent variable, which is Ex. So that is a bad sign. Then what about error correction term? How much is this one? 20.69%. 20.69%. It means that error correction term actually correct the disequilibrium of the system. I am telling again, error correction term actually correct the disequilibrium of the system. That is her task. That is her job. Okay, here the speed at which she is correcting disequilibrium is 20.69% annually. Here we have the annual data, right? The data we are using in this model is annual data. So error correction term, she is correcting the disequilibrium at the rate of 20.69% annually. Speed of adjustment is 20.69% annually. Right. In other way, she is adjusting with the previous period disequilibrium at the rate of 20.69%. Or in other way, speed of adjustment of the disequilibrium is 20.69%. That is the meaning of the error correction term. But here there are two things is good. The sign is negative and it is significant because the p-value is 1.34%, which is less than 5%. And when the p-value is less than 5%, then that particular variable becomes significant. So here error correction term is a significant. Okay, it has negative sign and also it is significant. It means that our EX and cons, it is giving validity when you lag one residual is significant and negative sign, it gives the validity that EX and cons have a long run equilibrium relationship, because error correction term is negative and significant. So it gives the validity that EX and cons have long run relationship. Okay. And finally, is this model is spurious? Spurious. So what is the guideline of spurious? The guideline of spurious is R square value should be greater than Durbin-Watson statistics. But here you can see R square value is smaller than Durbin-Watson statistics, meaning that our error correction model is not a spurious model, or our error correction model is not a nonsense model. We can accept the model. All right. Okay, now what do you want to check further? Suppose we want to check whether this error correction model has a serial correlation or not. That you want to check, right? Whether the residuals are serially correlated or not. That we want to check, right? How to check? I go to view, I go to residual diagnostic, I go to serial correlation LM test, right? So I click here, and here is already 2 lag. Okay, I take it 2 lag, then I okay. So it is the Bruce-Godfrey serial correlation test, and normally we choose observed R square and corresponding p-value. What is the p-value? P-value is less than 5%, meaning that we reject null hypothesis and accept alternative hypothesis. And what is our alternative hypothesis? Alternative hypothesis is that model is serially correlated, or our error correction model is serially correlated. or the residual of the error correction model is serially correlated. So meaning that our error correction model has a problem. What is the problem? The model is suffering from serial correlation, which is not desirable. Okay, then we check whether the residual is normally distributed or not. I check the normal distribution. Go to view, residual test, then test of normality. I click here. The result has come up. The Jarkabera statistics and the p-value, right? You can see from here. Jarkabera and p-value. What is the p-value? P-value is less than 5%. So meaning that we can reject null hypothesis and accept alternative. What is our alternative hypothesis? Alternative hypothesis is the residual is not normal. The residual of the error correction model is not normally distributed, but that is not desirable. What is the desirable? Residual should be normally distributed. That is desirable. But here in our error correction model, residual is not normally distributed. So here we have two problems. One problem, error correction model is suffering from serial correlation, and second problem is that the residual is not normally distributed, which is not desirable. So these are the bad side of our error correction model. So these are the bad sides. So we have to design our model, our error correction model, in a such a way so that these two problems cannot come up. Right? We have to do something. We have to do something so that serial correlation or not normal residual do not come up. We have to do that. So that is the end of the story, and yeah. So here I have just shown ECM, but in other place I have shown the VECM, right? In our other place, may not be here. Okay, what I'm showing here, I'm telling the whole story one by one, that I already just I'm giving the whole things at a time. You can see from here, right? Just I start from here. Okay, so the whole model, the whole story that I said previously. Okay, I just adjust it first a little bit, then I come back to you. Okay, adjust slightly. Okay, here I am taking the whole picture that I said today. Is coming up gradually, right? So here you can see the whole model: spurious regression, co-integration, and error correction model. So here is the total thing is here. So gradually you can see. So I gradually go down and you can see the whole thing again.